Hi everyone, welcome to lesson 2 of pre-calculus. I decided to go ahead and make a video of this lesson so students who maybe are just struggling a little bit here in the beginning until you get used to the pace and used to the different problems. Maybe you want to go back and re-watch some of the examples from class. I'm also making a video for those of you who are off island or for those of you who are in a hotel and you're quarantined for 14 days and you haven't quite gotten out yet and you're having a hard time following the Zoom lesson. So I just thought it would be better if you had a video that you could go back and reference as you work your way through these first couple of lessons in pre-calculus. So we're at lesson 2, which is about higher degree polynomials and inequalities. Let's have a look at these objectives and then I'll take you through the examples. So objective number 1. We're going to learn how to describe the end behavior of a function by looking at the degree and looking at the leading coefficient. So the degree of a polynomial and the leading coefficient of the polynomial, are going to be very helpful because you're going to know what the end behavior is. And if you know what the end behavior is, that's going to help you graph the polynomial function. So you're going to eventually sketch graphs of these polynomial functions, and you're going to do that by considering the multiplicity of roots. That means, is it a double root? Is it a triple root? Is it a single root? You're also going to take into consideration the degree of the polynomial, and then that degree of the polynomial allows you to know or describe what its end behavior is, and the leading coefficient, of course, will also have a little part of that. We are going to learn something called the intermediate value theorem, and this intermediate value theorem is going to allow us to locate zeros and determine the degree of a polynomial. So we'll have a few at least one example problem addressing that. And finally, our last few examples in this lesson are going to be about solving polynomial inequalities. All right, so let's jump into our warm-up. So warm-up says fully factor the cubic function and then sketch the graph. So sketch just means, sketch means we're going to sketch it. Notice there's no specific values on this X and Y axis, so you're just gonna put some values on and do a quick sketch. So how do we fully factor this cubic function? So notice there's 4 terms, so hopefully your instinct is to factor by grouping. So if I group the first 2 and I group the second 2, so I'm going to group the first 2, I'm going to group the second 2. So my first 2 has an x squared in common. So I get x minus 15. My second 2, I'm going to pull out a negative 4, right? I'm going to factor out a negative 4, so that's going to become x minus 15. So remember, when you factor by grouping, these parentheses should be identical to each other because now that's our greatest common factor. So we would factor out the x minus 15. What do we have left over? We have our x squared minus 4. Okay, that's still not fully factored because x squared minus 4 is the difference of squares. We can factor that further by making it x plus 2, x minus 2. So why do we do that? We do that so that we can find all of our zeros, right? This indicates that we have a 0 at 15, we have a 0 at 2, we have a 0 at negative 2. So I'm going to go here at negative 2, I'm going to put a 2, I'm going to put a 15, and I know that my graph is going to go through those 3 points. What other important point could we put on here? Again, this is a warm-up, but let's look. What else could we do? Well, hopefully you're saying to yourself, let's look at the original problem. I have my x-intercepts, right? These are our x-intercepts, but what about our y-intercept? That's super easy. You put in 0 for x, 0 for x, 0 for x. What is our y-intercept? Our y-intercept is 60. So now we have that point on our graph. Okay, the last thing you should be thinking to yourself is, well, what kind of function is this? It's a cubic function. And if it is a cubic function, wrong mode there, sorry. If it's a cubic function, that means it has the shape of something like this, especially if there's a positive leading coefficient. So see up here, all of this is very important. The degree, it's a cubic. The leading coefficient, it's positive, so that means my graph is going to be increasing from left to right. So now I know I'm going to go up through the -2, up to 60, down through the 2. We don't know how far down we're going to go, but we don't care. You don't need to put that point here on your graph. So this is a sketch of the graph, and you're done. Okay, next we're going to talk about the fundamental theorem of algebra. So the fundamental theorem of algebra is just very simple. It says a polynomial function of degree n will have exactly n complex roots. So if you have an equation that is x to the 5th power, that means you have exactly 5 complex roots. If you have n to the 3rd power, that means you have exactly 3 complex roots. So we talked about complex roots in our first lesson. So one of the things I just want to remind you of about complex roots is that if you have irrational roots, right? So if roots are irrational, then irrational roots will come in pairs, and then imaginary roots will also come in pairs. Real roots, however, do not come in pairs. Okay, so we are only going to study polynomial functions with rational coefficients, just so you know, and so all of this applies to polynomial functions with rational coefficients. Okay, so if we have a linear function, that's y equals mx plus b, right? A linear function means you just have x to the 1st power. So it doesn't matter what we happen to have here. X is to the 1st power. Oops, that means that it's going to only cross the x-axis at one point. You are going to have one real root. Your graph could be anything, but a linear function is going to cross the x-axis at one point. A quadratic function, that means you have ax squared plus bx plus c, so you have x squared, so you should have 2 roots. You either have 2 real roots, right? That's a parabola going through at 2 locations on the x-axis. You could have 1 real double root, right? So a double root means it's going to come down, hit the x-axis, and bounce away. So that is a double root. So when it bounces away, it's called a double, or it's an even root. It's some kind of multiplicity, and we'll talk more about that later. Okay, what if we have imaginary roots? So imaginary roots means the graph is never going to cross the x-axis. So that could be your vertex is above the x-axis and it's opening upward, or the vertex is below the x-axis, it's opening downward. So it would never cross the x-axis. So instead you would have 2 imaginary roots. For this section, you have a cubic function, which is y equals x cubed, a quartic function, y equals x to the 4th. I would say just pause the video and try to sketch a few graphs that have 3 real roots, or 1 real root and 2 imaginary roots, or 4 real roots, and see how many graphs you can sketch to make them as different as they can be. Think multiple roots, like double roots in there, and when you're done, unpause and kind of look through and compare what you drew to what I draw. Okay, so have a look. There's a combination of single roots, double roots. This is by no means all of the different types of combinations you could have or sketches. Of course, there's an infinite amount, so just have a quick look. You can look at the answer key to get a better idea. Yeah, if you're not understanding, like imaginary roots come in pairs, or that you can have double roots, triple roots, quadruple roots, right? Even quadruple roots. And you're not sure what that looks like, then ask your teacher. They can clarify some of the specifics. Okay, so let's talk more specifically about the multiplicity of a root, right? So multiplicity of a root. So root has multiplicity, which refers to the number of times its associated factor appears in the polynomial. So here, if you have x minus 5, the quantity squared, then that means 5 is a double root. Now something specific happens in our graph when we have even roots versus odd roots, single roots versus triple roots versus double roots versus quadruple roots. So this information here is going to be very helpful when you are sketching your graph. So you're going to refer back to this probably until you get the hang of it. So it says the multiplicity of a root affects the shape of the graph of a polynomial. If a root has odd multiplicity, the graph will cross through the x-axis at that root. So if it appears an odd number of times, then the graph will cross through at that root. If the root appears an even amount of times or has even multiplicity, then the graph will bounce away at that root. It will not cross through, it will touch it at that numerical value. That'll be an x-intercept, but then it will bounce away and go back the direction that it was coming from. So it will not cross. So let's kind of experiment, or let's do an example here so you can see what I mean by this. So we have this function y equals 3x times x plus 5, the quantity cubed, times x plus 2 times x minus 1, the quantity squared. So here we have an x in front. So this 0, it says list the roots with their multiplicities. So this is 0. This root is 0. It's only to the first power, so that's a single root. For this x plus 5, this means we have a root of -5, and that x plus 5 root occurs, or factor occurs 3 times. So that means that this 5, -5, is a triple root. Then we have x plus 2. So this is to the first power out up here. So we have x equals -2, and that's back to a single root again. And then we're at our last one, which is x equals 1, and it's raised to the second power, so that is a double root. So first of all, I would encourage you to sketch those or graph those roots on your sketch over here, because now our next stage is to sketch the graph. So on your x-axis, we need to have a -5. So this is our -5 root. We need to have a 0. We need to have a -2, and we need to have 1. So we have a 0 root, a -5 root, a -2 root, and a 1 root. All right, now in order to sketch, we need to know what the overall degree is, right? So we need to know the overall degree. So this is to the first power. This was to x to the third power, x to the first power, x to the second power. So that's x to the first power, x to the third power, x to the first power, and x to the second power. So all together, that would be x to the 7th power. So that is an odd exponent. Our leading coefficient is positive, therefore, right, so our leading coefficient here is a +3, and this x is positive, this x is positive, this x is positive, this x is positive. So I have a leading coefficient of 3, it's positive, it's an odd exponent, so that means your end behavior here, it should be, as it gets smaller, it should be getting smaller. Sorry, as x coordinate gets lower, the y coordinate should be getting smaller as well. As the x coordinate gets bigger, the y coordinate should be getting bigger as well, right? A negative number to an odd exponent is going to become negative, and even number to an odd exponent is going to stay positive. So we'll talk about end behavior here in our next one, but what do we have then? Well, our graph, we're going to come, if it needs to end, so this is going to end down over here, this is going to end up over here, because it's an odd exponent. So right here at -5, we have a triple root. So it comes through and it flattens out here, and it continues to go up. And then at -2, we have a single root. So it's going to come up and then it's going to go straight down. And then at 0, it's also a single root. So it's going to come up, go through 0. And at 1, it's a double root. So it's going to come down, bounce away, and then continue upward. So this was a single root. This was a double root. So the double root, according to this right here, right, it bounces off. Now all of this should make sense. Your directions should make sense. If it's an odd exponent, an odd degree, then then your end behavior, your graph is going to look like this with the leading positive coefficient. So we're going to get into more of those details in our next example. Okay, I lied. Sorry, we're talking about turning points next. So a turning point is an x value. Is when an x value has a maximum or a minimum where that occurs. So a turning point is an x value where a minimum or a maximum occurs, because when it turns, it's going from an increasing part of the function to a decreasing part of the function, right? This is obviously a maximum. And then a decreasing part of the function to an increasing part of the function, this is a minimum, right? So it's your maximums and minimums, not the absolute, but that's okay. We can still have maximums and minimums in that general area. So a polynomial with n turning points will have a degree of at least n plus 1. So if it has 5 turning points, then it will have a degree of 6 at a minimum. Okay, that's what that means. So it says, consider the polynomial graphed below. State the minimum possible degree of the polynomial by observing the number of turning points. So again, decreasing to increasing, this is a turning point. Increasing to decreasing, this is a turning point. Decreasing to increasing, this is a turning point. But now look at the rest of the graph. If you were walking this on a hill, like it says here, uphill, downhill, you would continue to go up, and it's never really changing from increasing to decreasing. It's just continuing to go up the whole time. So it looks like we have 3 turning points, and if we have 3 turning points, then we have a minimum degree of x to the 4th power. Now that doesn't mean we have a degree of x to the 4th power. That's the minimum it can possibly be. So letter B says, determine the likely multiplicity of each root and write the equation for the polynomial. So we have a we have a root at -3, so that's an x plus 3. Because it's bouncing away, we have a minimum there of a double root. Then we have a root here at 0. It goes through the x-axis at 0, so I'm going to put that in front because that's just an x by itself. It's going straight through, there's no flattening out, so I'm going to call that a single root, so it's x to the 1st power. And then we have a flattening out here. It looks like it's at 4, so that would be an x minus 4, and because it's going through the graph, but it's flattening out, that has a minimum degree, or it appears a minimum of a triple root. So for my overall function, it looks like I have x times x plus 3, the quantity squared, times x minus 4, the quantity cubed. Now, do we know if that's the exact function? No, because we didn't give you any other point on the graph. So we don't know what the stretch factor is, but that's okay. So what is the minimum degree, or sorry, what does it look like the degree is? It looks like it's an x to the 6th, because it's 1, and then x squared, then x to the 3rd. But we knew it has a minimum degree of x to the 4th, but it could have been bigger. Now try this one on your own. It says, given a polynomial of degree 6, which of the following could be its graph? So just circle all that applies. So go ahead and pause and do that on your own, and then compare it with the answer key or with this video, and as soon as you're done. Okay, did you get A, C, E, and H? If not, have a look at the answer key or talk to your teacher. Okay, so now let's talk about end behavior. Right, so what is end behavior? It says how a graph behaves for very large values of x or very small values of x is called end behavior. So really we're going to be looking for as x goes to infinity or as x goes to negative infinity. So those negative numbers are getting larger and larger and larger, but technically they're negative, so they're getting smaller and smaller and smaller in value. So here we have this little diagram here. It says determine the end behavior of a polynomial function. We look at both the degree of the polynomial and its leading coefficients. Remember a sub n, that's talking about the leading coefficient. So if the leading coefficient, so right here, this is referring to the leading coefficient. So I put that here to remind you in case you don't know what the a sub n is representing. So if the leading coefficient for an odd degreed polynomial, if that leading coefficient is positive, then what happens? Right, so that's like saying if y equals x cubed and we had a positive leading coefficient of like 2. Well, as you put in a larger and larger and larger x value, so if I put in 100, right, then it's going to be 2 times 100 cubed. If I put in 500, then it's going to be 2 times 500 cubed. So those y values are getting bigger and bigger and bigger, and they're staying positive. So as x gets larger and larger and larger, y gets larger and larger and larger as a positive number. So as x is positive and going to infinity, y is going to positive infinity. As x is getting smaller and smaller and smaller, if we put in a negative value, so if I put in a negative 100, right, well, a negative cubed stays negative. So now, as my x values are getting smaller and smaller and smaller negatively, then my y values are also negative. So this written work right here is representing end behavior. As x goes to infinity, y goes to infinity. As x goes to negative infinity, then the function, or what the y values of the function, go toward negative infinity. Now, if your leading coefficient is negative, right? So if my leading coefficient was negative 2x cubed, well, the exact opposite's going to happen. Because when I put in a positive 100, it stays positive, but I'm multiplying it by a negative 2. So now as x gets, we put in bigger positive values, the y values get smaller or go to negative infinity. If you put in negative x values, those y values go to positive infinity. So the leading coefficient matters because in your head you should be thinking end behaviors of what is the shape of that graph going to be. With an even function, think parabola, right? If you have y equals x squared, or if you have y equals negative x squared, well, if the leading coefficient is positive, it opens up on both sides. If the leading coefficient is negative, then it goes down on both sides. So it opens up, so these are going to go to positive infinity. If it's a negative leading coefficient, then they're both going to go to negative infinity. Okay, let's talk about the intermediate value theorem. This is the original definition of the intermediate value theorem. It says if f of x is continuous. So if a function is continuous over some interval a to b, so those are x values, right? So they're calling this is a, so this is from a to b. This is a, this is b. So if the function is continuous between those two x values, and k is a number between the two y values, so my f of b is up here, my f of a is down here. So there's at least one number in between these two y values that will equal k, right? So there's at least one x value in between that's going to equal that value k in between f of b and f of a. Okay, what does that mean? How did I read that again? Just kind of go through it. So specifically what this is telling you is if you plug in f of b and you get a positive y result, and then you plug in f of a and you get a negative y result, well, if your y value goes from a negative to a positive, but it is continuous, then it must have crossed the x-axis, so you must have an x-intercept somewhere between f of a and f of b. That's what the intermediate value theorem tells you. Right? So it allows you to approximate the location of your x-intercept or your zero or your root, whatever you're going to call this specific point where it crosses the x-axis. Right? If you go from a negative at 2 to a positive y value at 3 point something, that means there's a 0 between 2 and 3 point something. So why is that useful? Well, it's useful for a question like number 4. So question number 4 says a polynomial has all of its roots on the interval from negative 4 to 4. All of its roots are real. One of them is a double root and one of them is a triple root. Use this information and the table of values below to determine the smallest possible degree for this polynomial. So we're trying to figure out, is it x to what power is the smallest possible degree? We know all of the roots are real. Check. we know one of them is a double root, so one of them is going to be an x squared. We know one of them is a triple root. We know one of them is going to be an x cubed. Okay, well, how do I know how many single roots there are? So the other thing that you need to make sure you're paying attention to is that we're trying to determine the smallest possible degree. Is this the only possible answer? No, it's just the smallest possible degree. So according to the intermediate value theorem, there's a 0 when you go from a positive y value to a negative y value, or from a negative y value to a positive y value. So if I look at this P of x is my y values. These are my x values. So I'm only going to look across the row at my y values right here. Okay, so this is a negative y value, stays negative y value. Doesn't necessarily cross the x-axis between these two values? No. But then you go from a negative y value to a positive y value. So it must cross the x-axis between -5 and 3. Sorry, between -3 and -2. My apologies. So it must cross the x-axis between -3 and -2. Now, my y value was a 3. My y value goes to a -11. So once again, it went from positive to negative. So we must have another cross of the x-axis between -2 and -1. Okay, hold on a second. One more time. I went from a negative y value to a positive y value. So once again, we must have a cross of the x-axis because it went from a negative y value to a positive y value. Okay, +7 goes to +4. Doesn't necessarily have to cross the x-axis. It could, but it doesn't necessarily. And because we're getting the smallest degree, we're not going to count that. +4 goes to -13. It must cross the x-axis right here. -13 goes to +5. Again, must cross the x-axis. +5 goes down to 1. Even though it goes down, doesn't necessarily mean it crosses the x-axis, so therefore I don't count that. Okay, now, if it crosses the x-axis, that means it's a minimum of what type of root? Hopefully you're saying to yourself that's a minimum of a single root. So it's one single root, one single root, one single root, one single root. But wait a minute. They told us that one of them was a triple root, and any odd amount of roots cross through the x-axis. They have to go through. So I can't count all of these as single roots because the directions at the beginning instructed us that there is at least one triple root. It doesn't even say at least. It says one of them is a triple root. So I have to take one of these singles and I have to make it a triple. Because it's an odd number, it goes through the axis from a negative to a positive or a positive to a negative y value. So now I have one single root, one single root, one single root, one single root, but then I have a triple root. Oops, x to the third power. So I have an x to the 1, x to the 1, x to the 1, and an x cubed. Oh, sorry, and one more x to the 1. My bad, I don't have enough room. I can't scroll this up. So I have 1, 2, 3, 4. I have my 1, 2, 3, 4, and I have my x to the third power. But lastly, I have to not forget about this double root. Can you tell where the double root occurs in my list of y values? No. And we actually don't care where it occurs. That's not what the question's asking us. The question is just asking us what is the minimum possible degree for this polynomial. Well, I have to tack on that double root because it exists. They told us that in the beginning instructions. So now I have a root of 1, 2, 3, 4, sorry, a degree, not a root, of 1, 2, 3, 4, 5, 6, 7, 8, 9. So this has a minimum degree, and I apologize for writing all over the place because I don't have space, minimum degree of 9. Oops. So it's a minimum of x to the 9th power. Again, if you're not sure about that, ask your teacher or look at some other examples, maybe in old quizzes or on the homework, and see if you can figure it out. The answer key also has a really nice written explanation, so you can check out the answer key to help you as well. Okay, and finally, we have our polynomial inequalities. So how do we solve for a polynomial inequality? Well, we're going to have to just identify the interval where the graph is above or below the x-axis based on our inequality sign. Is it a greater than or equal to sign, less than or equal to sign? So I'll do the first example for you, or I'll just do all of them. We'll see how it goes. So step number one is you're going to have to factor, right? So we're going to move the x squared's positive. I want to keep the x squared positive, so I'm going to move my 4x and my 5 to the other side. So it becomes positive 4x and then minus 5. I am going to factor this. So it's plus 5 minus 1 to get the positive 4 in the middle and the negative 5. So it multiplies to give us negative 5, adds to give us positive 4. So I'm going to do a quick sketch of this polynomial. I have a 0 at negative 5 and a 0 at 1, so I know it goes through those 2 points. It's a quadratic with a leading coefficient of positive. So it means it's a parabola, and it's just going through those 2 zeros, and it's opening up. Now, this is the function right here. So in other words, it's saying 0 is greater than or equal to this function. I like to read it from left to right. Most math teachers are going to say, okay, where is the function, right? We're reading it from left to right, so I'm going to move my y value to the other side. I'm going to reverse the way it's written. So the function, when is the function going to be less than or equal to 0? So the function is less than or equal to 0. Those y values are down here on the lower part. So what is that x coordinate wise? Well, that's from between negative 5 and 1. Now, because I have an inclusive sign here, it's less than or equal to, then I'm going to include the negative 5 and the 1, or I can do it in my bracket notation, so we would accept either of these answers. So when will the function be less than or equal to 0? When x is caught between negative 5 and 1, including negative 5 and 1. So either of these ways, you can write it. So example number 2 is really nice. They have already factored, it's already in factored form. So I have a 0 at negative 3. I have a 0 at 2. I have a 0 at negative 1. So I probably should have spread those out a little bit more, but that's okay. Now the last thing I have to do is to figure out what this, what the degree of this polynomial is, So we're going to have x to the second power. I'm going to have x to the third power, and I'm going to have x to the invisible 1 power. So x squared times x cubed times x to the 1 is x to the 6th power. So this is an even function, which means my end behaviors are either ending in up, up, or they're ending in down, down. Look at the leading coefficient. If the leading coefficient is negative, then it must be opening down, down. So I'm going to put that on my paper just to remind myself. Now, my graph has to go through negative 3, it has to go through negative 1, and it has to go through 2. At negative 3, I have a double root, so it's going to go up and bounce away. At negative 1, it's a single root, so it's going to go up and it's going to go through. At positive 2, it's a triple root, right? So I have a triple root, I have a double root, and I have a single root. So the triple root says it's going to come down, and usually it flattens out through a multiple odd root, like a triple root or a to the 5th power quintuple root. It's going to flatten out a bit. So lastly, sorry as I've drawn all over this right here, the last thing we need to do is we need to figure out, okay, when is the y value, this is the function, when is that function less than 0? So the function is less than 0 here, here, and here, right? So how do we write that as our answer? Well, it's less than 0, that is exclusive. So we're going to have from negative infinity to negative 3. We have to exclude negative 3, so we go from negative 3 to negative 1. Again, rounded parentheses because we're excluding those values. or your union or your U is like an or statement, or it's going from 2 to positive infinity. So your answer is from negative infinity to negative 3, negative 3 to negative 1, and 2 to infinity. C and D are the same type of problem, except this time you have to factor first. Notice they're the same factoring, except they have a different inequality sign. So the answers will be different, but your process of factoring is the same. So I would go ahead and pause, try to factor it on your own. There are 4 terms, so you're going to factor by grouping. So here, I'm going to do this one first, but I'm going to have that same factoring question over on letter D. It's just I changed the inequality sign, so it's x cubed plus 2x squared minus 4x. I move my 8 over, but now it's less than or equal to 0. So factor by grouping, see how you do, sketch the graph, compare with this video as soon as you're done. Okay, for the first one, did you get negative 2, x equals negative 2, and then you had to say 2 to infinity for when it's greater than or equal to 0, and for when it's less than or equal to 0, you should have just gotten from negative infinity to 2. Here's the sketch of the graph, here's the factoring, so check through all of that. You can pause your video, look and see if you have the same work, and if you have the same answer. That was a lot, again, so make sure you're asking your teacher questions if you have any. Bye.